Hello everyone. We're going to get started with some problems that demonstrate how to use, so the topic of today is FTC II in new contexts. So jumping right in to our first example, it says big F of x is given as the integral from -1 to x of this function 2t squared minus 5t minus 12dt. And just keeping in mind that this is very normal to have these letters, the t's here, but then the x in the area function, and really those t's are just a dummy variable and they do not matter. But the question says, over what interval is big F of x increasing? Later we'll find where it's concave, its minima, point of inflection, and so on. So this problem really is a mishmash of our current unit and then the previous unit where we did a whole lot of increasing, decreasing, concavity. So let's get one thing straight first of all. There is a difference, and you need to know this. There is a big difference between big F of x and little f of x, and it's just a mathematical convention. But big F of x will refer to our integral, aka our area function. As you know, the integral gives us the area under a curve. So if f of x, let's say if this was f of x, was this curve right here, then f of x gives me where I am on the curve at different x values, but big f of x would give me the area under the curve from my lower limit to my upper limit. So they are different. We need to keep that distinction in mind. So when I say, where is big f of x increasing, you need to recall the definitions of where functions are increasing and so on. So let's take a trip back down memory lane. Okay, I would like you to copy this down and try to fill it in yourself. But I'll start you off. If any function is increasing, any function at all, whether it's f, big F, g, x of x, gosh, who knows? If any function is increasing, then its slopes should be positive. Right? If it's increasing, that means the slopes are greater than 0. They're positive. And if any function is decreasing, that means that its slopes or its derivative are going to be less than 0. And it goes the same backwards. If some slope or if some derivative is greater than 0, that means that the original function was increasing. So if I said g prime of x is greater than 0, that means g of x is increasing. If I said big H double prime of x is greater than 0, that means that big H prime of x is increasing. So you see I'm going back by one derivative. Okay, so let's continue on. If I have a relative minimum, so let's imagine the relative min, that means that the slopes were decreasing and then they changed to increasing. Oh, sorry, not the slopes. That means that the function was decreasing and it changed to be increasing, meaning that the slopes switch from negative to positive. That's a relative min. If I have a relative max, on the other hand, that means that the slopes from left to right switched from being positive to being negative. Next, if f of x has a critical point, that means that the slope either is 0 or does not exist. So this is what I mean by that. Here, my slopes are 0 because they're not positive, they're not negative, they're the turning point. So those are where slopes is 0, aka a horizontal tangent line. Then here is where my slope does not exist, at a sharp corner and also at vertical tangents. Okay, those are all considered critical points. Next, if f of x is concave up, so if everything we've done so far was dealing with the first derivative, then once we enter the realm of concavity, we start looking at the second derivative. So if it's concave up, the second derivative is greater than 0, And if any function, f, g, h, is concave down, then its double derivative is less than 0. And finally, if f of x has an inflection point, a point of inflection, well, that means that the second derivative, okay, it's twofold, has to equal 0, and it switches signs. So it's not enough positive to negative or negative to positive. So it's not enough for the second derivative to equal 0. This, I would say, was the most common mistake on your final from semester 1, which was just setting it equal to 0. But you also have to check that it switches signs from left to right. Okay, so now that we have our definitions refreshed in our brain, let's go back. The question says, where is big F of x increasing? Well, where is anything increasing? If anything is increasing, then its slopes should be positive. And so what I want you to notice right now is that all of a sudden, so we were dealing with f of x, which is an integral, but now all of a sudden we're dealing with the derivative of the integral. Does this look familiar? This might come back easier. If I have the derivative of an integral, FTC II immediately kicks in. So as a reminder, this is the definition of FTC II. FTC II says if you're taking the derivative of an integral, then you will plug in the upper limit first, f of g of x, times the derivative of the upper limit. Write this down, put it in a box. This is FTC II, the definition. Minus, then you'll plug in the lower limit, parentheses. You'll plug in the lower limit, so it'll be f of the whole function, h of x, times the derivative of h of x. So put this in a box, super important. That's the definition of FTC II. The most common mistake here is forgetting this part, times the derivative. And even I make the mistake sometimes when I'm rushing in my teaching, but you will not because we've gone over it. So when you're taking the derivative of an integral, you have to remember this here refers to the chain rule that would happen when you're taking the derivative. All right, so continuing on. Since we are, in fact, taking the derivative of the integral big F of x, we need to use FTC II. So off to the side, we're going to set it up. So big F prime of x is really nothing more than, so we're going to plug in the upper limit into t. So I'll get 2x squared instead of t, minus 5x, minus 12. All of that times, FTC II says times the derivative times 1. Minus, now we're plugging in the lower limit, which is negative 1. So see if you can think ahead. If I plug in negative 1 everywhere, let's say it goes right here, but then we're going to multiply by the derivative of negative 1, which is 0. And so we discussed this before. When we're plugging in, when one of our limits is a constant, then that portion is just going to be 0. So we're just going to write minus 0. So essentially, this is my f prime of x. Big F prime of x is just 2x squared minus 5x minus 12. All right, and I want to see where that is positive. Well, how do I always determine if something is positive or negative? Number line. We'll use the number line. So let us go ahead and magic X. Go ahead and do it yourself. I'm looking for two numbers that multiply to, don't forget the number in front, multiplies to negative 24, but adds to negative 5. 8 and 3, watch your signs. Okay, since there was a number in front, we're going to divide both by that number. Okay, this is our little shortcut. And simplify, that becomes negative 4. So we'll write x. And this, we add an x at the bottom. It didn't simplify, so we get 2x, and reading it up, plus 3. From here, we get our zeros. So let's label this number line, always important to label. We have a 0 at 4 and a 0 at negative 3/2. We're starting at the right side positive, and then we're going to flip and flip all the way across. And the question said, where is big F increasing? So that means big F prime should be greater than 0. Our answer will be this section here. So going into our answers, we would say on the interval from negative infinity to negative 3/2, and then from 4 until infinity. Sweet. And that's it. You just have to remember your definition and then apply it in this new context. Let's go to B. It says find the critical point of f of x. So again, what's the critical point of any function? Well, critical point is where the derivative either equals 0 or does not exist. Hey, we already found f prime of x. We found it right here. So where is this guy equal to 0? Well, we got at x equals 4 and x equals negative 3/2. Those are where? If I were to set this equal to 0, that's where I would get those answers. And since this is a polynomial, in fact, it is a parabola, right? It's a parabola, so we can see, because polynomials will never have, it does not exist. Right? The slope exists everywhere. This graph is continuous. Next, let's move on to concave down. So if anything is concave down, in this case, big F. If big F is concave down, that means that big F double prime should be less than 0. Well, so far we found f prime of x. I'm going to, by the way, keep my notes organized by highlighting the important parts. If that's big F prime of x, then big F double prime of x is going to be just the derivative of that. So it'll be 4x minus 5, and then the 12 will disappear. And I'll be concave down. Well, let's set this equal to 0. And we get x equals 5 over 4. That shall be our number line. And starting positive and then flipping negative. And I'm concave down where f double prime is less than 0. So we want this region right here on negative infinity to 5/4. All right, let's move on to relative minima. So try writing the definition of relative minima yourself without peeking. Imagine in your mind what a minimum looks like. So if you said that big F prime changes, the slopes of the function, meaning we're taking the first derivative, changes from negative to positive, then you'd be right. So let's see where we change from negative to positive on the first derivative. So we're looking right over here. I change from negative to positive at x equals 4. Notice that I have not only my answer, but also the explanation for every problem. These are all my explanations. So you will never just have an answer. You will always start with an explanation. E, point of inflection. Where does that occur? Point of inflection for any function occurs where the derivative, the double derivative of that function equals 0 or does not exist. Oh, sorry, no, I'm mixing up that with critical point. The point of inflection is where it equals 0, the double derivative, 0, and it has to switch signs. So we're examining our second derivative. I'm highlighting it now. Our second derivative equals 0, and it switches signs at x equals 5 over 4. Simple as that. Next, where is the graph decreasing and concave up? So I wasn't expecting this because I didn't look ahead, but indeed, okay, first let me label. I must do a double number line. So I'm going to bring my number line from up top down below so that I can line them up. -3/2 is to the left of 5/4, and +4 is greater than 5/4, so I'm aligning them. Next, I'm going to extend my positives and negatives all the way across. So do this with me. It's not a futile exercise. It's actually really helpful and prevents many students from making errors, myself included. Okay, then you'll drop the connecting lines. And now we want to see where we're decreasing, so let's write what that means. Any function is decreasing. So if big F is decreasing, that means its slopes shall be less than 0. And if it's concave up, that means its double derivative is greater than 0. So I want the first derivative negative. So I'm looking here. But I also want the second derivative to be positive. So this is the only section that works from from 5 over 4 until 4. That's where the first derivative is negative and the second derivative is positive. So we shall write on the interval from 5/4 until 4. And here, as always, is our explanation. We never leave it behind. Beautiful. So this problem is timed to take around 10 minutes. It took a little longer because we're explaining and remembering all the formulas, but on your homework you will study the formulas first so that you can do the problems without peeking. All right, let's do one more, this time a graph problem. So this guy gives us a graph that in the first sentence they say the graph of f of x, so this is f of x, label it, is given below. Then they give us a new function, and they call that function g of x, which is the area function of f. So if f is my curve, g is the guy that's going to tell me how much area is under my curve as we move along. From 2 to any x value. All right, so the first thing that you'll notice is I'm asking for the increasing interval. My increasing interval, it says find where, g of x is increasing. So it's important to know, is it g that's increasing or is it f that's increasing? And indeed it says where is g increasing? Well, g will be increasing where its derivative is greater than 0. But notice that we don't know where the, notice right away that since g is an integral right here, and now we're dealing with its derivative right here, what immediately kicks into play when I'm doing the derivative of the integral? If you said FTC II, you'd be right. So we're going to show some work down below of our FTC II. And just immediately, let's be smart and do the work up front. The derivative of g is, let's use FTC II. We're going to plug in x first everywhere we see a t. Times 1. Minus, we're plugging in the 2 next. Times 0. Oh, but we discussed this before. When we're plugging in a constant, that just becomes 0. So g prime of x is just f of x. Oh my god. The derivative of our integral function right here is actually just this curve. Interesting. And for good measure, because I'm looking ahead and I see concavity questions, let's go ahead and just take it one step further. G double prime of x. I want to know what that is, so I'll take one more derivative. Well, hey, if I take one more derivative on the left side of the equal sign, then I can take one derivative on the right side of the equal sign, and now I still have a true statement. So these two are going to be my guiding statements for the rest of this problem. Okay, these two right here. This is the first thing you want to do on problems like this, is just immediately write your G prime and your G double prime. Okay, let's jump in now. A says, where is G increasing? So that means that G prime of x, which, by the way, we know from right here, is f of x, should be greater than 0. And oh my gosh, this function is f of x. So if I want to know where f of x is greater than 0, I'm looking above the x-axis. I'm interested in this region right here. This is where f of x is greater than 0. So we'll say from, or on the interval from 1 till, the instructions say to call that 3-point monkey. Something, 3-point something, who knows? Might as well call it monkey. And next, let's do decreasing interval. So if g of x is decreasing, that means its slope should be less than 0. But the derivative of g is f of x. Again, we already discovered that right here. And so I want you to focus on this part. Okay, I'm helping you, I'm guiding you. Don't worry about that. Just focus on the fact, hey, I have a graph. I want to see where that graph is less than 0. Well, now my answer will be from 0 to 1. And from, try it yourself. Yeah, 3-point monkey until 6-point monkey. Or a 6-point donkey. And that's how we approach these problems. Let's do B. It says, where are we concave up? Well, for anything to be concave up, its double derivative is greater than 0. So if g is concave up, that means g's double derivative should be greater than 0. But the double derivative of g, oh my gosh, look here, it's just f prime. So the second derivative of g, which is the first derivative of f, should be greater than 0. Okay, now slow down for a second. So we're focusing, again, our graph is in terms of f, so we don't want this, we're going to focus here. If f prime of x is greater than 0, that means that the slopes of f are positive. Oh my god, that means that f should be increasing, right? We've talked about this before, but write it down right now. The difference between f of x is greater than 0 and f prime of x is greater than 0 is really important. You need to know what they mean. If f of x and f of x alone is greater than 0, that means we're looking above the axis. But if I say f prime of x is greater than 0, that means I'm looking for where it's increasing, or where it has a positive slope. Right? So this is where f prime of x is greater than 0. But this, in black, is where f of x is greater than 0. Let me say that again. This red section is where f prime of x is greater than 0, because it's increasing. The slopes are positive. Also here, the slopes are positive. But in black is where just f of x is greater than 0. So keep that in mind. And now let's answer this question on B. Okay, so I'm concave up where f prime is greater than 0, so I'm looking for where f is increasing. F is increasing from, let's call that 0.5 until 2. And also it's increasing from left to right, so now it's falling, and then it's increasing from 5 till 6-point donkey. So on. we said 0.5 to 2. And then from 5 to 6 point donkey. Try the next one yourself. Okay, pause the video right now. So it's concave down. G will be concave down where it's double derivative, which is the first derivative of x from here is less than 0. So again, we're focusing only on the f portion because we have the graph. And if f prime is less than 0, that means that the slopes of f are negative. That means that f is decreasing. So I'm interested in this portion here. From 2 until 5. Okay, let's do our relative max now. Again, relative max. The relative max of G means that G prime changes from positive to negative. But G prime is the same as F. And so we're looking where F then changes from positive to negative. F changes from positive to negative? Careful. Why don't you answer this? Is it here? 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 Or here? Where does F change from positive to negative? The answer is C. F changes from positive to negative where it's going from above the axis to below the axis. And so our answer is 3 point donkey. 3 point monkey. 3 point orangutan, who cares? Okay, next we have relative min. Relative min occurs where G prime, right, the first derivative. If I said where's the relative min of H, then you would write, well, H prime changes. If I said, what's the relative min of H double prime? Well, the relative min of that is where H, its derivative. So then we'd be dealing with the third derivative. So it's always one derivative away, okay? The relative min of G is where G prime, which is f of x, changes. So it was negative and then positive. And we change from negative to positive, right here. I'm below the axis, I'm negative. I'm above the axis, I'm positive. Okay, some crazy stuff is happening around downtown right now. But we shall ignore, we shall persevere. At x equals 1. Again, I'm helping you. I want you to only focus on this portion of the explanation when you're looking for an answer. All right, let's do our inflection point. Inflection point deals with first derivative or second? You're so smart. You said the second. Good. So, we want the inflection point of G. I'm being crazy right now. The inflection point of G. That means that G double prime equals 0 and it switches signs. Okay, but we're dealing in terms of our f function. So G double prime is just another way of saying f prime. So it's where f prime of x equals 0 and switches signs. And as we've done before, we're going to ignore the G explanation. We're going to focus on the f explanation. And it says where f prime of x equals 0. Well, if this is f, what's it mean for f prime to equal 0? Think. What's another word for f prime? What's another word for the derivative? It's the slope. That means that the slopes of f are 0. Here's where the slope is 0. Because it was negative slope to the left, a positive slope to the right, but it's 0 at that point. Where else are the slopes equal to 0? Oh, right there. That's a horizontal tangent line. Right there. That's another horizontal tangent line. And f prime should switch signs. So observe. Here, f prime, aka the slope of f, is negative. Here, the slopes are positive. So it does indeed switch signs. Let's call that x equals 0.5. If here the slopes are positive of f, And here the slopes are negative. That means we also switch signs at x equals 2. Okay, so f prime is less than 0. And now, again, this is f. So f prime, or the slopes, are positive here, greater than 0. We also switch signs at x equals 5. I'm going to write that in black because it's hard to see. So we have 3 points of inflection for g. At x equals 0.5, 2, and 5. Great, now let's do increasing and concave down. So we're required to write our definitions first. Increasing is where g prime of x, which is f of x, is greater than 0. And concave down of g means that g double prime of x, which is f prime of x, should be less than 0. And as always, we're ignoring the g explanation. We're focusing on the f. So I want to know, where is f greater than 0? Let me clean up my graph a little bit. Why don't you try this yourself while I'm cleaning? Seriously, take a minute. Think through the next couple problems yourself. Okay, so f of x is greater than 0 here. But f prime of x has to be less than 0. That means that the graph has to be, since this is f, then f prime means the slopes should be negative. And that's only true in this region. It's where the graph itself is positive, but then its slopes are negative. So our answer is from 2 to 3-point monkey. Try the next one yourself. Start with your explanation. So decreasing means g prime of x, which is f of x. Decreasing means less than 0. And then concave up for g means its double derivative, which is the first derivative of f, should be, concave up means greater than 0. Circle what matters, cross out what doesn't. F of x is less than 0. While I'm cleaning, you write your answer. F of x is less than 0. That means that we're below the axis. So we're looking here and here. But then f prime greater than 0 means the slope of f should be positive. So our final answer is the only places that satisfy both those conditions are going to be from 0.5 till 1 and 5 to 6-point donkey. And we're done. So, good job if you made it this far. Give yourself a pat on the back. This wasn't easy, especially doing it on video. If this was a review, good for you. I'm glad that you kept your formulas close. Here's the big important point I want to make before we go. Whenever you find yourself dealing with an integral function right here, and you find yourself having to take the derivative because it's asking, hey, where is that function increasing? So immediately you're taking the derivative. Whenever you're taking the derivative or the second derivative of an integral, first remember to apply FTC II. Don't forget the part where you need to multiply by the slopes. Remember, if it's a constant, it just becomes 0. But actually write the 0, please. And then for these graphs, I want you to immediately put these in a box so that every problem down the line, you can just look there, and it makes your life so much easier than trying to figure it out for each problem individually. All right, that's all I have to say. I hope that this was helpful, and have a great day.